We're going to start today with a warm-up problem. A kid throws a rock straight down off a cliff that's 45 meters above the surface of the water with an initial speed of 8.4 meters per second. How long does it take for the rock to make a splash? So, in other words, how much time passes between when the rock leaves the kid's hand and when it hits the surface of the water 45 meters later? Then tell me, what is the speed just before impact? Go ahead, pause the screen, try this, and we will go over it in a moment. As always, we should start with listing out our known values. So we have, let's start my list here. Kid throws a rock straight down. Okay, that's going to tell me the direction of my initial velocity of a cliff that is 45 meters above the surface of the water. So the rock travels down 45 meters. So my displacement, delta x, is negative 45 meters. With the initial speed, all right, so my initial velocity then would be 8.4 meters per second down. That's why I have that negative sign there. My acceleration would be given by Earth's free fall acceleration of negative 9.81 meters per second squared. Part A is asking me to find the time, delta t. So I want to think about the kinematics equation that relates these four values together, and that would be the one that does not have v final, the one that looks like this. Delta x equals v initial times delta t plus 1/2 a t squared. And I can plug in, well, actually, this is my quadratic. Oh, great. I get to use a quadratic formula again. All right, so let me go ahead and rearrange this equation to have delta x on the other side. I'm going to put this in the format that I'm used to, where I have a coefficient a times, the variable squared plus bx plus c, or whatever it is. So we have 0 equals 1/2. A is negative 9.81 times my unknown squared plus vi delta t would be negative 8.4 times delta t, and then minus a negative 45, which would be plus 45. Now I'm going to go ahead and simplify it a bit. 0.5 times 9.81 gives me 4.91, so negative 4.91 times delta t squared plus negative 8.4 times delta t. I'm going to keep these coefficients in parentheses, plus 45. All right, so my coefficient A is negative 4.91, my coefficient B is negative 8.4, and my coefficient C is, or my constant rather, C is 45. So the quadratic formula says negative b plus or minus the square root of b squared minus 4ac all over 2a. And I can plug it in. Negative 8.4 means positive 8.4 plus or minus the square root of negative 8.4 squared is just going to become, well, it's the same thing as 8.4 squared. So we'll do that. Times minus 4. A is negative 4.91. And then C is 45. All right, so, and that's all over 2 times negative 4.91. All right, so let me do the discriminant first. 8.4, can you see my calculator? Yeah, 8.4 squared minus, actually, we're going to do plus because that's negative 4 times negative 4.91. So 4 times 4.91 times 45. And that is the square root I need. So we have our first option will be 8.4 plus 31. I'm just going to use 31 divided by 2. So divided by negative 9.81. And our next option would be 8.4 minus 31 over negative 9.81. So option 1 and option 2. So this gives us negative 4.0, and this is time, so seconds. And our second one would be 8.4 minus 31 divided by negative 9.81 gives us positive 2.3 seconds. So our answer would be positive 2.3 seconds. All right, the next piece of this problem is finding the speed just before impact. So we can go ahead and look up at our known values. We have that delta t is equal to 2.3 seconds. That's right before it hits the surface of the water. So I can use really any of the kinematics equations that have v final in it. I'll use this one, v final equals v initial plus a delta t, and I'll go ahead and plug in. The initial was negative 8.4 plus acceleration is due to gravity, so negative 9.81, and our delta t is 2.3 seconds. So we have 9.81 times 2.3, and then we have negative 8.4 minus that answer. So negative 30.9 or negative 31 meters per second. And I should note that it makes sense to have a negative value as my final velocity because this rock is traveling down. All right, we're going to move on to talking about vector properties. Vectors can be represented within vector diagrams. So this is a very useful thing that we'll do where we are looking to analyze a situation and we'll use a vector diagram. And in these diagrams, we draw vectors as arrows. So the size of the arrow tells you the relative magnitude, and the direction that the arrow points in tells you the direction that that vector acts in. So for instance, if you had one vector that was 2 miles per hour north, so this is should be a vector that represents velocity, and a second vector that's 4 miles per hour west, they might look something like this, where we have something pointing up, because conventionally for our compass we have north as up, east as to the right, down would be south, and west would be to the left. So here I have a northward vector, so it's going to point up like this, 2 miles per hour north, and then I have a westward vector right here, 4 miles per hour, and it's pointed in the left direction. Now, the important part here is the magnitude, right? Or, I mean, magnitude and direction are both equally important, but the one that's maybe less obvious is that the magnitude of this vector is twice the magnitude of this vector. So this arrow representing 4 miles per hour west should be twice as long as the one that represents 2 miles per hour north. So if I asked you a question like this, which diagram shows the car accelerating? Well, you would be able to look at this and you'd say, it's got to be diagram 2, because these are velocity vector arrows. And for diagram 1, those arrows are all staying the same size, which means that the magnitude of the velocity or the speed is remaining constant. Versus diagram 2, the size of the arrows is increasing, meaning the magnitude of the velocity is getting larger or it's speeding up. If I ask you a question like this, vector A is 15 meters per second north. What is the approximate magnitude and direction of vector B? Well, you could look at this and say, vector B looks like it's maybe twice as tall as vector A, so I would probably say 30 meters per second north. And since the lines are parallel, that's where I got my north direction from, because it's also pointed up. Vectors can be added in any order. When you add vectors together, this is called vector addition. It's going to be the majority of what we talk about in today's lesson. The sum of 2 or more vectors is called the resultant. And when you subtract a vector, it's the same thing as adding the vector's negative. A vector's negative points the opposite direction. So for example, if vector A looks like this, the negative of vector A would be 180 degrees, and but the same size. So I take the tip of that arrow and I stick it down there on the other end. So a vector and its negative are parallel. When you multiply or divide by a vector by a scalar, you get a vector. So for instance, if you have a vector b that's pointed to the right, when you have 2b, that would be also pointed to the right, and the magnitude is twice that original vector b magnitude. The direction of a two-dimensional vector is given by the angle theta. So 2 dimensions, as implied by this statement here, means that our vectors don't necessarily lie on the x or y axis, but often they're at angles. So for example, we have a displacement vector here, 2 meters at some angle theta relative to the positive x-axis or east here. So this is a Greek symbol theta, This red arrow indicates the magnitude of my displacement vector, and this angle theta is the direction. So the direction is up from east here. It's pretty common that you'll see angles measured from the positive x-axis, but that's not always the case. So we have to be really careful as we work with two-dimensional vectors to make sure we understand where that angle, if an angle is given, is it measured from the x or the y, and kind of what that implies about the trigonometric functions we'll use to solve for these quantities. So, for example, if this angle theta was 45 degrees, we might say that this displacement vector is 2 meters at 45 degrees up from east. And here's a little animation. Thank you from the physics classroom, which is a great website for resources if you need extra help. And it's just showing you conventionally the angles as measured from the positive x-axis. Again, they're not always measured from the positive x-axis, but that is usually how you see them written, and so this animation is just going through that. Okay, try this problem. Rocky walks 5 miles east and then 7 miles north. What is the magnitude and direction of his displacement? Go ahead and pause it. All right, so this problem is going to need to use, we're going to need to use some trig to solve this problem. So the dimensions were 5 east, 7 up. So we went over 5, up 7. So it might look something like that if I were to try to draw it to scale. Right, 5 east is what he walked, and then up 7. So here is the actual displacement vector that Rocky drew. And this is just the displacements that he used to get there. So 5 east, 7 north. Well, I should get that. It's 5 miles east, 7 miles north. Now we're looking to find the magnitude, so the size of this vector, and the direction theta, and we'll give it relative to the positive axis. So here we have a right triangle, and it's a right triangle with one of the legs is 5 units and the other one as 7. So first thing we should do is solve for the hypotenuse h here, and we can use Pythagorean theorem. Pythagorean theorem, of course, is a squared plus b squared equals c squared, which means that to find c, the hypotenuse, we'll take the square root of a squared plus b squared. That is the square root of 5 squared plus 7 squared, or the square root of 25 plus 49. Which is 8.6. So 8.6 miles would be the magnitude of the displacement. And now I need the direction. So let's think about our trig. We have angle theta here. This is our opposite side. This is our adjacent side. The trigonometric function that relates O and A is tangent. So what that means is that the tangent of angle theta equals the opposite over the adjacent side lengths. So the tangent of our unknown is equal to 7 over 5. But we need to isolate theta, so we should do the inverse operation of both sides. So, we should do the inverse tan function to both sides because I want to get theta alone. So the inverse tangent of tan theta is theta. So I take the inverse tan of both sides. I get theta equals 54 degrees. So my answer here would be that the displacement vector for Rocky is 8.6 miles at an angle of 54 degrees up from east. And like I said before, oftentimes you'll see that if the direction is measured relative to east, that people leave that part out. But I'm gonna keep it for now, just for clarification, because we will get into problems where we see angles measured down from north and things like that. Next thing that I'll point out is if you are getting funky answers for your angle theta, you may be in the wrong mode. So you could be in radian or degree mode on your calculators. Regardless of if it's the same calculator as me, you could be using one online, but still it probably has the option for radian degrees. So quick way to check that is the tangent of 45 should be 1 if you're in degree mode. It should be 1.6 if you're in radian mode. So like I said before, we are going to talk about adding vectors. Now, vectors are not the same as scalars. Vectors have direction. So adding vectors is not the same as adding scalars. This right here, what I'm going over, is the graphical method of vector addition. This is known as the tip-to-tail method of vector addition. So the way you do this is you take the arrows that represent those vectors and you arrange them one by one, head to tail. So if you're adding 4 vectors, you take them all, you don't change the magnitude, you don't change the direction, and you line them up so they're head to tail in any order. The resultant vector is drawn connecting the first and last vector, tail to tail, head to head. So, for example, if we have vectors A and B, which they look like they have pretty much the same magnitude, vector B is north, vector A is east. Let's find the vector sum of A and B. Let's find the resultant for vector A minus vector B. Let's find the resultant of vector B minus vector A. And then let's find 2A plus B. Go ahead and pause now. Give this a shot. Okay, so here are my 2 vectors. B is pointed up, A is pointed to the right. And the first problem I'm asked to do is to find their vector sum. A plus B. So I'm going to align these 2 vectors up, tip to tail. And I'm not going to change their magnitude. I'm not going to change their direction. So I can move them around parallel to each other anywhere on this paper. So let's see, B, keeping the magnitude the same, plus A. Here's them added tip to tail, and the resultant connects the first and last vector together, tail to tail, tip to tip. That would be my resultant, which I'm going to just show as my R for resultant here. So you can imagine if, I don't know, we had 2 force vectors. One is pulling up on an object, one is pulling rightward on the object. The vector sum of those 2 forces is going to be upward and rightward. The next piece was A minus B. So I'm going to take vector A, and I'm going to line it up tip to tail with the negative of B. B points up, so the negative is going to be the same size, but pointed down. Like that. And now I connect the first and last vector, tip to tip, tail to tail. And I'm going to mark that R for resultant. You know what? Let's do this. Let's call this, let's say A plus B equals R1. A minus B equals R2. And then I'll label them R1 and R2. Now we have B minus A. So let's take vector B and let's line it up tip to tail with a negative A. A points right, the negative A is the same size, pointed left. So tip to tip, tail to tail gives me a resultant, R3. That's 180 degrees of this one here. So be careful. That is not the same operation as that. Last one was 2A plus B. That's going to equal R4. So 2A would be same direction, double the magnitude. So hopefully that arrow looks about twice the size of that arrow. And I'm adding that to B, which points up, so I'll add it right here. And my result is drawn, tail to tail, tip to tip, tail to tail, tip to tip, like that. So it could be really useful to know the graphical method of vector addition. So adding them in that tip to tail fashion is very useful. You'll see that we will do that quite a bit. But of course, we are going to be also needing to know how to solve vector addition problems algebraically. So, using real numbers. And for this practice, I'm going to start off by talking about how vectors in 2 dimensions can be broken down into their components. The word component means parts. So when I say that vectors in 2 dimensions can be broken down into 2 components, I'm saying that they have 2 parts, one in each dimension. So if you have a vector that's along the xy plane, like this one, maybe, right, the northeast plane, then you would have one in the x direction and one in the y direction. Or, back to this example, you have a component of this that's eastward and a component that's northward. So, for instance, vector A, shown in black here, has a horizontal component and a vertical component. And vector A is the vector sum of the x component plus the y component. So if you look at this diagram here, right, vector A is made up of 2 parts. There's a y part and an x part. And if you add the x part and the y part, or the horizontal and the vertical components together in a tip to tail fashion, you would see that vector A is the resultant vector. Right? If I added these 2 things together in a tip to tail fashion, then draw tail to tail, tip to tip, this would be the resultant. That's what this means right here. It's the vector sum. So you can think about vector components like, imagine that vector A had some depth to it. And I took a flashlight and I shined the flashlight towards the y-axis. So the light was coming in this direction. This vector A would create a shadow on the y-axis that was this high. And if I, likewise, right, if I took a flashlight and I shined down on vector A, it would create a shadow on the x-axis that looked like this, the x component. All vectors that are in 2 dimensions have 2 parts to them. If you have a northwest vector, it would have a northward vector and a westward vector. And again, if you imagine adding these 2 vectors up in a tip to tail fashion, that is the resultant. An upward rightward vector has an upward and rightward part. So take a moment and draw and label the components of each of these vectors. Okay, here are my 4 vectors, and I'm tasked with drawing the x and y components of each of these vectors. So I'm going to imagine that they fall in they stem from the origin, right? So if I imagine that this is the origin on an XY graph where I'm saying, okay, the y-axis is, I don't know, parallel to my paper, which is fine. You don't have to do that, but you can. But if I were to say, okay, this is a 2-dimensional vector that has some x and y component, and the y-axis is here, then the y component of vector A comes up also from the origin to a height right here, and I can label that AY. And same thing with B. Goes up to the same height, and we can call that BY. CY would be down here, and DY would be like this. Now, let's draw the x components. So AX, BX, CX, DX. Oops, maybe I drew DX a little long. It should probably have ended here. I went overboard with that one, so maybe here. Now, if I asked you to tell me, well, actually, let me label these things. A, B, C, and D. And if I said, I don't know, which of these vectors, I guess I didn't need to label them because they are A, B, C, and D. But anywho, which of these vectors has a negative y component. And that would be the two that are pointed down, right? C and D. If I said, which of these vectors have a positive x component? Well, that would be these two, B and C, right? They're both, the x components are pointed right. If I said, which of these vectors is in, I don't know, quadrant 2? That's this one, right? And if you don't know exactly what I'm talking about because you don't remember the convention for labeling the XY coordinate system in the quadrants, that's okay. That's not super important. But what is important from this exercise is, one, identifying the magnitude, so the size of the x and y components, and two, knowing which ones are negative, right? So a two-dimensional vector such as vector B can be broken up into x and y components that are either positive or negative. And in the case of B, we have a positive y and a positive x component. In the case of C, we have a positive x and a negative y. So what we just did here, where we broke each of these two-dimensional vectors into their x and y components, that's called resolving a vector. So taking something that's in 2 dimensions and breaking it up into x and y parts is a really useful tool, and it's referred to as resolving vectors. So for example, you know, this image is also from the physics classroom because they do a really good job with this unit on 2D motion. But imagine you have a dog that has a leash on it, and the leash is being pulled upward and rightward with some force. There's a situation where you could have a rightward and upward force, so there's 2 leashes acting on the dog, and if they're pulled with a very specific upward and a very specific rightward force, this dog would not be able to tell the difference between this situation and this situation. So this vector, represented by the red arrow, that would be a force vector, is mathematically equivalent to the sum of these 2 force vectors. And that's useful because we are going to be solving kinematics problems where we need to be resolving a 2-dimensional vector into its x and y components in order to be able to properly analyze it. So try this. A dog on a leash is being pulled with a force of 60 newtons at an angle of 45 degrees, and that is 45 degrees, up from east. Solve for the vertical and horizontal components of the force vector. We had 60 newtons at an angle of 40 degrees to east. So our x and y components look like this. This would be I'm going to just call this vector D for vector dog. And this would be dy, and dx would look something like this. Now to find the magnitude of those values, we can use our trig. So we have dx would be, let's see, if this were rearranged in a tip-to-tail fashion, we would see that this is a right triangle, where dy would be my opposite, dx would be my adjacent, and 60 newtons, or d, would be my hypotenuse. So if I want to find the x component, I would need to relate my known information on the hypotenuse h to the adjacent side and then to my angle 40. So the trigonometric function, the trigonometric function that relates a and h is cosine. So for example, the cosine of angle theta equals a over h. If I'm trying to solve for a, then I can do so by multiplying h by cosine theta. So dx is going to be 60 times the cosine of 40. (46 newtons). And that is x, that would be to the right. You can also show that as a positive 46 newtons, is fine. Now the y component is going to be found by trying to relate, well actually I can, now that I have 2 sides of the right triangle, I could do a bunch of different things. I could use Pythagorean theorem. I could use my tangent function, or I can use my sine function, which is what I'm going to do. I'm going to try to relate my hypotenuse 60 newtons to my opposite side. So the function that relates h and o is sine. So sine of angle theta equals o over h. And that means that if I want to solve for o, I take h and I multiply by sine theta. So that would be 60 times the sine of 40, which is 38.5 or 39 newtons up. Now, real quick, not super important here, but this is 1 sig fig and 1 sig fig. So it would be more proper to say that my x component is, let's say, positive 50 newtons, and my y component is positive 40 newtons. So we can make a general rule for if you have a two-dimensional vector that is measured up from east, we can say the following things are true. And I really want to make sure we understand that this is true if theta is measured from the horizontal positive axis. So if theta lies right here, then the following three things are true. If theta is measured down from the y-axis, then these are not true anymore. And again, maybe we'll look at some problems in a bit that have theta measured down from the y. You know, when that happens, when it's not measured up from the x, you can either derive again the trigonometric functions you would use, or look closely at your right triangles and figure out which trigonometric function to use, or you can take 90 degrees minus that angle theta and then just, use the angle that is right here. So anywho, to find the horizontal component AX when theta is measured from horizontal positive axis, use A cosine theta. To find the vertical component, use A sine theta. And to find the magnitude of A, well, this is Pythagorean theorem right here. You take the square root of the x component squared plus the y component squared. Right, so if you know the x and y components of vector A, then you can solve for vector A by using Pythagorean theorem. And I hope that's clear because, again, if you arrange these two components in a tip-to-tail fashion, you would see that vector A is the resultant. Okay, here's a problem in 2 dimensions. We have a lizard running with a speed of 0.61 meters per second towards you when it crosses a walking sidewalk moving with a leftward velocity of 1.3 meters per second. A walking sidewalk is one of those things that, like, if you guys have ever been to an airport, it's just like a conveyor belt on the floor. Tell me the magnitude of the velocity of the lizard as viewed from above. Now, I would say, pause and go ahead and try this problem. What you could also do is you could wait a moment for me to kind of set this problem up on my paper, and then you can pause it there and try to solve for it. All right, I'm going to draw a little picture here just because it helps to draw a picture and then to simplify that picture into a vector diagram after. But the question says, okay, it's walking towards you. So I don't know. Here's you, I guess, or me, whatever. And here is our moving sidewalk, and the velocity of that sidewalk is leftward. You're at rest. And then the lizard walks across this, right? So here's the lizard. Terrible lizard. And he's moving across in this direction. So if I were to add these vectors in a tip-to-tail fashion, and I should draw them to scale. So let me check out those magnitudes again. The lizard is running, let's say velocity of the lizard would be, here it's positive 0.61 meters per second. And the velocity of the sidewalk would be leftward, 1.3 meters per second. And to find the actual velocity that the lizard moves, if you're if you're looking from above the situation, he would take a path that's in this direction, right? Because he's walking straight while the moving sidewalk is pulling him this direction. So if you were looking at the situation from above you would see him moving in a path that looked like that. And that is what we're looking for in this problem. We're trying to find the velocity as viewed from above, which would be the vector sum of these two. So the lizard's velocity vector looks like that. The moving sidewalk has a velocity vector that looks like that. And our resultant vector is going to look like this. So, as you notice, this is the hypotenuse of a right triangle, which means that we can use Pythagorean theorem to solve for the magnitude of the velocity vector. And I'm looking back at my question now. I'm not asked for direction, which is great. So all I need to do then is plug in to my Pythagorean theorem equation. So 1.4 meters per second would be the magnitude of the velocity or the speed of the lizard as viewed from above. So that last problem, we were adding two one-dimensional vectors that were perpendicular to each other. And, it's pretty straightforward for finding the magnitude of the result, and you use Pythagorean theorem. Now, what we're going to be doing often in our practice with two-dimensional motion is we're going to be adding together two-dimensional vectors. And it's not as clean as just sticking them tip to tail and using Pythagorean theorem, because when you add them in that tip to tail fashion, you'll often notice that they don't make a right triangle. So we have to do something a little bit different. And before I show you the rules of adding two-dimensional vectors, I want to take a look real quick at what it looks like graphically, and maybe that will help us understand the algebraic rules. All right, so let's look at these two vectors, and I'm going to assume that they're on a coordinate where the x axis is parallel to the top of my paper and the y is parallel to the edge of my paper. Now, it doesn't really matter, but that's the convention I'm going to use for the purpose of this demonstration. So I have vector b and vector a, and because of this convention, I would say that these are both two-dimensional. They have an x and y component. What I want to show you is that adding these two vectors together you get the same answer as adding their x components together and then adding their y components together and then finding the magnitude of the resultant that way. So first, I just want to show you what the resultant looks like when I add these things together in a tip-to-tail fashion. So let's go down here. I'm going to do my best to draw B exactly as I see it here. So parallel, same direction, and the same magnitude. And then A is right here. I'm going to add this tip to tail. It's about this long, maybe a little tiny bit longer. Here's my A. So the resultant, I will draw in blue here, connecting my first and last vectors together. I'll label that as resultant R. So what I'm trying to show you is that you can get this answer by breaking down A and B into their constituent parts and adding those parts independently. So first, let me just draw BY and AY. I'll label those. And I'll use a different color to draw BX and AX. So what I'm going to do now is I'm going to add this vector, this vector, this vector, and this vector together, and I will show you that I get the same answer here as vector R. So it doesn't matter which order I add these four components together in, and I would encourage you guys to practice that. Try different orders of adding these vectors together, and you should see that you get this vector every time. So I'm going to pick a random order to add them just based on the space that I have. So I don't know, I'll start with by here. So again, let's see, make sure this and this are the same size. Let me just add ay onto that as well. So I have by plus ay looks like this plus this. And now I'll add their x components together as well. All right, so I'll start with taking ay, stick it right here. Maybe it's a little bit longer than what I have. And then by is 180 degrees. So I could add that tip to tail right here, but that makes me feel like it's going to get a little not so clear when I have it overlapping. So I'm just going to stick it down here instead. So B faces to the right, and it's this long. Maybe that's a little long even. So here's my AY, and here's my BY. Now I will connect the first and last vectors together, and that will give me the magnitude and direction of my resultant vector R. So hopefully you can see that these two resultant vectors are the same magnitude and the same direction, which means they're the same vector. So to summarize, when you add two or more vectors, the resultant vector can be found by adding up the components of the two vectors. So for instance, if vector A plus vector B equals vector R, then the x component of vector R is equal to the x component of A plus the x component of B, and the y component of R is equal to the y component of A plus the y component of B. Now, if you're adding multiple vectors, what you want to do is you want to start by resolving each vector into its components. That is, taking vector A, finding the x and the y components of vector A, and also taking vector B, finding the x and y components of B. And then you add all the x components together. Add all the y components together. These two totals are the components for the resultant vector. So the resultant vector would have an x component that is the vector sum of all the x components added together. And likewise, the y component of the resultant vector would be equal to the y components of all the vectors added together. Then you use those components to find the magnitude of the resultant. That's using Pythagorean theorem, because now you have the x and y components of your resultant. And then you can find the angle of the resultant using your trigonometric functions. You don't have to use the tangent function, but if you have the x and y components, well, the tangent function is what would be easiest to use, because you don't need to solve for the hypotenuse first. I'll talk more about that when we do a problem. So, for example, add these two vectors together. Find the magnitude and the direction of the resultant. Pause it here. Try this out in your notes. All right, I'm going to start with drawing out my vectors because I'm going to quickly just, draw a graphical addition of the two vectors so that I can compare my algebraic answer to my diagram. But to do that, as I'm looking back on my slide, those two vectors were not drawn to scale, right? 13 newtons should be over twice the length of 5 newtons. So I might redraw them here to scale. Here's my 5 newtons, and that should be somewhere between, and it's at 90 degrees to the east. It should be somewhere between 1/2 and 1/3 of my 13 newtons, which was at 70 degrees. So maybe 70 degrees down from east. So maybe something like that. And I'm going to add these two vectors together. So I'm just going to give them a label. We'll say, we'll call this vector A, and we'll call this vector B. Now, quickly arranging them in a tip-to-tail fashion. Here's A plus B. Gives me a resultant that looks something like this, which hopefully is what I get. All right, now on to algebraically solving it. So the resultant vector R is the vector sum of A and B, which means that the x component of vector R is the x component of A plus the x component of B. Now, quickly, as I look up at my diagram, there is no x component of vector B, right? It lies entirely on the y-axis, at least if I'm using a convention where this is my x and this is my y. You don't have to use that convention, but it's easy. And for the purpose of this demonstration, that is what I'm going to do. So my x component is 0. The y component then would be 5 sine 90, right, which is 5 times 1, or 5 newtons. Over here, the x component of A looks like this, and the y component of A looks like this. And the x component of A would be found by doing 13 cosine 70. And even though I'm not measured up from east, if you measure from the x-axis, you'll find that cosine is the proper function to use to relate the hypotenuse 13 to this side, or this component. If you are measuring, if you're using 30 from the y-axis, you would have a different function here. And maybe take a second and explore that a little bit if you'd like. You can get the same answer using 30, but the x component would be 13 sine 30. Anyways, AY is found by taking 13 sine of 70. And AY points down, so that's a negative. That's an important thing to remember. And it's often hard to, or it's easy to forget that. Okay, so the x component is going to be AX is 13 cosine 70, and then BX is 0. So 4 newtons is my x component. And that would be in the positive direction. Now the y component is going to be 5. Oh, sorry, AX. So we'll start with this one. Negative 13 sine 70 plus 5. So negative 7.21. So that negative sign means the y component should point down, right? So when you add this value to my 5, it should point down. And the resultant magnitude is found by taking the square root of this guy squared plus this guy squared, right? R equals the square root of x squared, the x component squared plus the y component squared. And then the angle theta would be found by, I can use the inverse tangent of the y component over the x component, right? Because if I have my x component is positive 4, and my y component is negative 7, then the resultant should look like that. And if I want to find the angle down from east, then I can use the inverse tangent of my opposite side, which is negative 7, or 7, divided by my adjacent, which is 4. And that should be the same as that. And even though I switched the color theme for some reason, it's shown, the resultant shown in blue here and red here, but they're the same direction, same magnitude. All right, so the square root of 16 plus 49, that's 4 squared plus 7 squared. 8. And the direction, inverse tangent of 7 over 4, 60 degrees. So my resultant vector is 8 newtons at an angle of 60 degrees. And that's 60 degrees down from east. I should have put that in there. Good work. So in physics, when we talk about motion in 2 dimensions, we are going to split up a 2-dimensional vector into its x and y components and analyze the motion in each dimension separately. It's one of the underlying principles of motion is that what happens in the x dimension is completely independent of what happens in the y dimension. This is a pretty interesting and pretty counterintuitive phenomenon. But for example, if I take a ball and I throw it in the air, the acceleration due to gravity affects only the y motion of the ball. The x motion of the ball, well, if it's in free fall, if there's no air resistance acting on it, then the x component of motion remains constant because there's nothing changing its motion. There's no acceleration in the x direction. So it's very useful for analyzing projectile motion, for example, if we know that what happens in the x direction and what happens in the y direction are independent of each other. So, as I sort of just mentioned, for projectile motion, which projectiles are objects that are thrown in the air at some angle. So they're also in free fall, meaning air resistance is negligible, but now they're acting in 2 dimensions. So for projectile motion, gravity influences only the vertical component of the object's motion. So the y component of acceleration would be negative 9.81 meters per second squared if this is a projectile on Earth. And the horizontal acceleration will be 0. Again, if this is a projectile on Earth, we have a uniform downward acceleration that acts, well, only downward. And so since there's no acceleration, nothing pushing or pulling on that object in the x dimension, then there would be nothing changing its motion. So we would say the acceleration, the x, is equal to 0. So for projectiles, you have negligible air resistance, meaning that nothing other than gravity pushes or pulls on it in the y dimension, and nothing at all pushes or pulls on it in the x dimension. So these 2 things will be true for our study on projectiles.